In this video, I will be demonstrating logistic growth models. Let's go back to the Diamond Lake example and ask the question, can the population of rainbow trout grow and grow unbounded? This is a graph from the previous video where we were modeling the population of rainbow trout that had been reintroduced using a geometric growth model. And what you can see from this curve is really the growth is, well, we say the growth is unbounded here. There's no boundary. It can keep growing and growing and growing and growing forever. And this is really not realistic. This is not how wildlife populations grow in general in nature. Another illustration that people often use or example is growing some kind of like bacteria in a petri dish. And the bacteria in that dish will grow geometrically, or sometimes we say exponentially. And in the textbook, it refers to exponential growth models as being pretty much synonymous with geometric growth models. But in any case, those going back to the petri dish idea, those bacteria can't grow to infinity in numbers. And what happens is, as more and more bacteria populate the medium that's being used to grow the bacteria in the petri dish, the growth rate slows down. The growth rate doesn't slow down. Well, I guess technically the growth rate slows down. And I'll show you how this works mathematically in a minute. Same thing's true of fish in a lake. I mean, fish need food to survive. They need dissolved oxygen in the water to survive. And so there will come a point at a certain density or number of fish where the growth rate will slow down. And one of the ideas is that these systems have what we call a carrying capacity. And we think of that as the maximum sustainable population. And this is an example of the logistic growth model. And it's given as a recursive equation or a recursive relationship here. And one of the things I want to talk about is how this is similar and different from the geometric growth model. So remember that the geometric growth model looks like this. When we write it in its recursive form, we have p sub n equal p sub n minus 1 plus r times p sub n minus 1. And so what this really does is this allows for, again, unlimited growth. So to regulate that growth and to account for, I wrote that wrong. I wrote logarithmic, logistic. The logistic growth model, written recursively, again, we have the population at year in this case, or time step in this, we're talking about years here in our example. So we still have the population in the previous year that we're adding to, going to add to that the amount that grow, or the amount that the population increases in the next year. But what we do is we introduce this factor p1 minus p sub n minus 1 over k times p n minus 1. So notice the two equations are really the same, except the logistic growth model has this extra factor. And let's think about what this does. What this does now, for the case of the Diamond Lake trout, I think we're going to say the carrying capacity is 1 million fish. So suppose we make that assumption. Then what we will do is we'll replace k with 1 million in the growth model. I need another 0 there. And think about what happens as the population each year gets closer to 1 million. this term in the difference gets closer and closer to 1. It'll approach 1. It'll get closer and closer to 1. It'll approach 1. And we say that is an asymptotic. It'll approach it asymptotically. It'll never quite get there. It'll get real close, though. Well, maybe it'll get there when n is infinity, but we're not going to wait an infinite number of years probably to see what happens here. The idea is, as p sub n gets larger, this fraction gets larger, and the difference between 1 and numbers getting closer to 1 gets smaller and smaller and approaches 0. So this term, what we say is this term approaches 0. Or I should call it a factor, really. I'm using a little shorthand notation because I'm running out of room here, but often we use this arrow to mean approaches. So this term, factor, I keep wanting to call it a term, it's a factor because it's being multiplied in the term. Make that clear. So what's being added here, this entire thing, is, we would call that a term. And this part of the term that's multiplying, we call that a factor. So anyway, that's the basic idea here. So now I want to go back and take a look at going into Excel now. And Excel is very powerful. It's very useful. I'm not going to spend a lot of time in this class on Excel. I mean, there are online classes students can take to learn Excel. YouTube is actually, I find myself, YouTube's a really great resource for learning how to use Excel more effectively. In any case, I will demonstrate how to look at this recursive process in Excel for Logistic. And one of the things is, the calculations become more and more cumbersome as the growth model gets more complex, and therefore it becomes more and more advantageous to use some kind of computer program. So in this table I've created in Excel, I've got time, okay, in years. It's going from first 0 year, the initial year, and then the next year is 1, 2, 3, and I have like 60 years right now in this table. And this is actually how I produced the plot that I was showing in the previous video. And what I'm going to put here in the next column is, again, number of trout, because this is what we're modeling. And in this case, we're going to talk about the logistic model. So in this case, we'll be working with the logistic model. And let's see, I want to wrap text and just doing a little bit of formatting stuff here. In a minute, that should, there we go. Just to make it look nice, or try to make it look nice. Okay, so as in the geometric growth model, we need to start off with an initial population. So I'm going to make that initial population 50,000 like it was in the previous example. Now, one of the really great things and powerful things about Excel is that I can put formulas in. I can define cells using formulas. So what I've done is I've just selected the next cell after my initial amount for time 0. And I'm going to move up to the fx bar. This is the function bar in Excel. I'm put my cursor right there, and I'm going to type equals. Anytime you're using formulas in Excel, you want to use a formula to set up a cell or do a calculation for a cell. You have to have that equal sign. That's something I often forget. All right, so C2. Now C2, notice here, this is column C. This is row 2. That's where the initial population of rainbow trout is located. And we're going to add to this. I'm just following the logistic growth model formula here. The next thing I would put in is the growth rate, and we're going to stick with the 6% per year growth rate. And this will be 1 minus now C2 again, because that is the previous year's population. It's going to be divided by 1 million. And then that whole quantity is multiplied again by, I don't know that I don't know that Excel recognizes what we call implied multiplication. So I'm just going to put the multiplication sign in there. I'm going to put them both in there, actually. I have multiplication here between the 6% and the logistic factor. All right, that looks right to me, so I'll press enter. So you can see already in the first year, the growth is slightly smaller than it would have been for the geometric model. Now Excel has a really nice feature. I can fill the rest of the cells year by year in this case by using what's called the fill feature. And if you look at my cursor right now, it's kind of like it's sort of like a cross that's open. I don't know how I would describe the cursor. But when I put the cursor over this corner of the cell that's selected, do you notice how it changes? Now it's not doing that down here because these cells are not selected. When it's selected, it'll do it. So when I put it up here and I move my cursor here, now I press and hold the mouse button, or in my case I'm using a trackpad, and I pull that box down and watch what happens. It's filled in with the calculation. I can look at any of the particular cells and I can check and see, yes, that is what I want. That's what I want Excel to do. And again, this is a recursive formula. So where each cell, this is cell C10, but it depends on C9's population. And you can see that's true all the way up. So what I'll do is go ahead and fill this all the way down. And you can see there's a bit of a difference now. The growth rate, when we look at a logistic model, is going to be quite a bit less. Now what I can do is compare these two. So I'm gonna just select all of these columns of numbers, and I'll go to Insert and then choose a scatter plot. And again, I'm not going to get really fancy with trying to format this or anything like that. I'm just, again, using Excel to demonstrate the difference between the two growth models and what's happening here. So you can see the blue dots represent, if you can see those dots in blue, but anyway, the dots along this curve are the geometric growth population densities, and then along the bottom or lower one, you can see that with the logistic growth model, these are starting to really flatten out. Now the carrying capacity is up here at 1 million, so the population here modeling of trout in the lake using a logistic model isn't really getting up to the carrying capacity in 60 years. So I'm going to actually extend this a little bit, and I can do that again easily in Excel. For this case over here, there's no formula for this column. This is just a sequence of numbers. And Excel will recognize the pattern. If I choose like the first three, say, and then use the fill feature, you can see off to the right there, it's telling me it's going to make the next one 61, 62, 63, and so on, which is exactly what I want. So I'm going to go out here to say, oh, let's go out 100 years and see what that looks like. So I'll do 100 years on that column. This one's based on a formula, so I don't think I need to pick the first three or anything, or the last three, but I will anyway. So now fill that in. Okay, wow, 16 million fish, 17 million fish in 100 years. That seems kind of unrealistic. But when we look at the logistic growth model, that number now is 955,162, getting close to 1 million. I want to extend this out, I think, even a little further, though, because I want to really show you what this curve looks like, the logistic curve. Sometimes it's referred to as an S curve, because it has a shape that's a S shape. I'll show you that in a minute here. All right, so we'll just fill these in. Now we're in the 120 years, according to the geometric growth model, we're up to 54,500,000 fish. But yeah, look, you know, with the logistic model, we're still below 1 million. And the reason is because it's been, the model is designed that way. And so again, let's just take a look at a scatter plot. And I'm going to select all three columns again, insert, scatter plot. All right, now this one's pretty drastically different. You can see that it's a huge difference between these two curves here. This one's just shooting off to, really off to infinity. And that's one of the problems with geometric models, is that in the long run, the model will predict the population going to infinity, which is just not realistic. So and the scaling's way off now. I mean, this thing's going up to like 60 million on the vertical axis maximum, and it's way beyond the 1 million carrying capacity that I had set. We had set the logistic growth model up for. So let's see. I'm going to try to draw just the logistic model this time. So I'm going to select the year. That's really my independent variable here. And then I'm going to just, if you press shift, oh wait, that didn't work. I got to remember how to do this. Hold on now. That was wrong. I think it's actually control, not shift. And I'm using a Mac too. I think the PCs are the same, but let's see, control. That wasn't it. What is it? Huh. Maybe it's, what is it? Is it option or command? Yeah, it's command. To remember which key is correct. So if you use the command key, I'm using a Macintosh, but like I said, I think the PCs work the same. But on a Mac, if you hold down the command key, you can select individual columns in Excel. And again, let's insert a scatter plot. So now, just looking at the logistic growth model, you can see that S curve beginning to take shape there. And what's happening is the population is reaching the carrying capacity. It's growing up to that carrying capacity, and it's going to, as we go off into the future, it'll flatten out even more and more. And I guess just for the heck of it, I can, since I'm in Excel now anyway, we can extend the years out even further. Like, I don't know. Let's go all the way out to 200 years. And see, it's so nice to have Excel, because all these calculations, Excel's just doing automatically and quickly. Be awful lot of calculations to do by hand, even using a calculator. Let's see, my graph go away. All right, let's see here. So, let's see. Okay, I need a new graph. All right, so pick that one. Do another scatter plot. And so now you can really see how the model is, the population under the logistic model is really growing rapidly at first. For the first 50 years or so, that population growth is pretty rapid, essentially geometric. But then that factor that we put into the recursive formula to slow the growth down really kicks in. And then the population just grows right on up to the carrying capacity. But see, it never quite gets there. It's close. It's at 999,903. And as we went into the future, we will get even closer yet. And that's what we think of as a stable population. When a population in nature reaches a carrying capacity and levels off, we say that the population's in equilibrium. So in any case, it looks good to me. That's it for this video. I hope it made sense, and please feel free to message me any questions. I'll see you in the next video.